you carry this ballast water. And this ballast water, now when you fill from the first port, okay, let me see the next. This is the ballast water cycle. After you discharge the cargo, you just take in the ballast water into this cargo hold. Now it is empty. You have water inside, okay? Then, Then from this first port, now this is during the voyage, and then second port, you fill the cargo hold, and before that you have to discharge this water. Step by step you discharge and then load the cargo. Now your cargo is full. Here your cargo was empty. Now see what you have done. For example, if this source port is in Sri Lanka, and if this last port is in the United States, what you have done? You have collected water from Sri Lanka and bring it to the United States. Think about the environment. Now, when you take this water in, you can't filter out all these small creatures in seawater. So these things will come inside. You bring them to United States, dump there. Now what will happen? No visa, just go over there, start invading. Okay? They start growing. Now this is what had happened. Now this zebra mussel. This one was initially from China, as I can remember. This is a water pipe. Now you can see this zebra mussel go to Canada, or United States and Canada, that area, and then start clogging the pipes. And this is the Chinese mitten crab. Now these crabs, they are very invasive. They start attacking the other animals, small animals in the native environment. And this is the European green crab. This European green crab travels from Europe to Australia and New Zealand. And this is one of the most dangerous creatures, cholera. You know this cholera, right? Now, it is said that in 1990s, that Gulf of Mexico, hundreds of small kids were dead due to this cholera, and they suspect ballast water carry this cholera from somewhere else to Mexico. Now what we have to do? Now this is the normal practice, ballast water exchange. What people are doing now is they just take ballast water from the source port. Generally ports are near the land, right? So very shallow water. You have lot of creatures at in the shallow water. Then they bring this water to the deep ocean, and then they discharge this water and take in deep ocean water. In deep ocean water, there are very small amount of animals are living. But this one is very, very risky. Can you imagine? They are discharging water and carrying in some other water, okay, new water into the cargo hold. If the sea is very rough, okay, then can you imagine how risky is this action? And then deballast. Now this one, people have found this practice is very, very inefficient. Okay, I don't have time to explain many things now. Now the International Maritime Organization is saying, treat it. If you don't treat, we will fine you. Okay. People are trying many methods, including heating, ultraviolet radiation, adding ozone, using a hydrocyclone and chlorine, filter them, ultrasonication, and combinations of these technologies. Sometimes people combine UV heat with ozonation and hydrocyclone like that. Okay. Now, we were thinking, can we do a simple thing without adding any of these chemicals? Okay, now if you want to do treatment system, you have to meet these standards. Meaning is, for example, you shouldn't have more than 10 organisms per cubic meter of this size. Okay, so you have to maintain these guidelines if your treatment system is accepted. Okay, and the timeline for implementation after 2016, you have no choice. You have to go and practice one of the treatment methods. So how many years more? Almost 4 years, right? 2011, this is the end. So after 4 years, you have to fix a treatment system to your ship. Now we propose electrochemical disinfection. I think you have learned electrolysis probably when you were in grade 9 or 10. Can you remember the electrolysis? Probably you will. This one? Have you done this? I think you must have done. When I was a child, I have done it. Okay. This is your water. You have 2 electrodes. Then here you will connect it to a current supply. Okay. At the anode, oxidation, cathode reduction. What is oxidation? I think you all know, very simple chemistry. What is it? Releasing electrons. So after anode release electrons, cathode will accept them. So here you have few equations. Now, can we use this simple cell to treat ballast water? Now, okay, why we want to do these electrochemical methods without practicing other UV radiation, ozonation and things like that? All the oxidants you can produce in situ, meaning is you don't have to carry any chemical, so you don't have to handle or store any chemical. Okay. And possibility of direct oxidation, meaning is some organisms will go and attach to your electrode and destroy on top of the electrode. Okay, simply like that. Then process control is very easy. Now, for example, now you can design many fantastic things, but who will use it? Okay, for example, you can build a nice filtration system or some gadget to treat water, and you can pass it to a person in Polonnaru, Anuradhapura or Hambantota or somewhere like that. What will happen next? Okay. Now people from that rural areas must know what will happen next. Most of the people are uneducated. If you give a long list of maintenance, that things like that, then after 1 year they will throw it away. Okay. So here this system is very easy to control. Okay, you can put one single switch and ask them to switch it on. Then for 5-10 years you can work with that. No need to change anything. Okay, that is the beauty of this technology. Okay, here I will share very simple small things with you, some very little amount of data. Now here is the optimized, we want to select the hydraulic retention time, meaning is after you fill your water into the reactor, how many minutes or hours you have to keep it inside. Now this ballasting process, sometimes 60,000 cubic meters you have to fill within 1 hour. Okay, can you imagine? The water flow is like, it's very quick process. So you can't wait for several minutes or hours. You have to treat it within very short time. I have found I can treat that water within 30 seconds. Okay, can you imagine how short it is? Then the next question is how much you have to apply, I mean the energy wise. The current was only 0.3 ampere. Finally my technology ends up like, to treat 1 cubic meter of ballast water you need only 0.3 0.001 kilowatts. Okay, so it is like 0.001 units. Now you know your electrical bill, right? So 0.001 unit comparison is like 0.001 units per 1 cubic meter. So most of our ship owners in Singapore were very happy to hear that. Total residual chlorine concentration was 1.5 milligrams per liter, so that you have some leftover chlorine after the reaction. This chlorine will kill leftover organisms. If you have any organism bypass your system, then this 1.5 you can use to kill that. Now this is the IMO guidelines. I have used only the E. coli data. Guideline was 250 CFU per 100 milliliter. Now we have achieved it. Why I have plotted this in 2 diagrams? Can you see the scale? Math students, why I have plotted these two in 2 diagrams? This is a log scale and this is a normal scale. Okay. Now if you plot all this data in one diagram without taking logarithms, then these points you can't see. Can you see this number 1 in 10 to the power 6? Okay. Okay. Now few images for you, scanning electron micrographs. Now, can you see the difference between these 2 figures? This is E. coli before disinfection. They are very nice. Can you see this rod shape? But after electrodisinfection, what had happened? Can you see the cell is damaged? Can you see it? Can you see some watery thing has come out? Can you see it? However, now I was very happy at this point. Now the things are dying, but my electrode also dying. So how can I work with this? Now this is before use, but after some time, lot of holes. Then what I did? I decided to, now I have to protect the anode from corrosion. Okay, now I have to learn some material sciences. Earlier I had to learn a lot of biology, microbiology and things like that. Remember, I was a civil engineer, okay, who did double maths, that pure mathematics and applied mathematics. Okay. Now I have to learn physics and chemistry again. Now if you enter faculty of engineering in any of these universities, after first you will not learn any chemistry. Okay. You will not learn physics after your first year. You will not learn mathematics after your 3rd year. Okay. So it is very different now. Lot of chemistry.